So these are just a couple examples from the textbook. So a girl sits at the top of a frictionless snow-covered hill on her inner tube. If the hill is inclined at an angle of 25 degrees to the horizontal, what will be the girl's acceleration due to gravity? Do you remember how this frictionless hill stuff works? Look, there's some cop cannons. You remember what happens on a frictionless hill? I mentioned it a few days ago. I know it's been kind of a weird kind of unit. You'll notice that the mass of the girl is not pointed out at all, is it? You don't need the mass, Connor? Why not? Hey? You saw something somewhere. Okay. Well, let me re-explain that a little bit, right? So if I draw this diagram, and we know that FD is down the plane like so, and it's frictionless, right? We do have a normal force, we do have a weight force, but we're only interested in the plane of down the hill, the direction, if we want to label that the x direction. Then in fact, the net force is equal to FD, right? And FD is equal to mg sine theta. But we don't have the mass. So sometimes, especially in grade 12 physics, we have to sort of deal with things where there's an unknown like that. So we're just going to leave it as an m. I'm going to say FD is equal to m times 9.8 times the sine of 25. And I guess I'll have to actually calculate that. (9.8) wake up call. 9.8 times the sine of 25. 4.14. So I'm going to say 4.14 m because I don't know the mass. 4.14 times m. And I'm trying to find acceleration, so I'm now going to say F net is equal to ma, and so this 4.14 m, because my FD and my F net are the same, is equal to ma, and guess what? The m's cancel, and the acceleration is 4.14 meters per second squared. Connor is right. The mass doesn't matter. Does that make sense? Yeah? Good, Blaine? Yeah? You might recall somewhere where I said that if it's a frictionless hill, A is equal to G sine theta, which is exactly what this is, 9.8 sine 25, right? Remember that? And I will say, I always say this after I do this example, it's all fun and games until Randy Greger loses his spleen on the tubing hill.
What was that?
When I was a kid, in behind the hospital in Meatwall, it was a convenient place for it. And behind the hospital, there's this big valley. Tanner knows where it is, all the way to the school there. And this local dude, local kind of. All right, let's talk about good old Evel Knievel. Yes, Martin's correct. Evel Knievel was a daredevil back in the 70s. The story is he broke every bone in his body at least once. He did some rather insane things, including this one here. Anyone ever been to Las Vegas?
Yeah.
There are fountains in front of Caesar's Palace looked like that back in the 70s. It's a little bit more grandiose now and kind of thing. It doesn't quite look like that, but there's this huge, huge fountain out front, and he decided to jump his motorbike over top. You're going to see a little bit of footage of that kind of thing. And then I will show you his most insane stunt of the 1970s. Always makes me laugh. So Evel Knievel is driving. His son is Robbie Knievel, who was a daredevil too. You may have heard of him. Evel Knievel is driving his motorcycle up a ramp inclined at 30 degrees to the horizontal before jumping over a row of cars. If there's a constant frictional force of 1,000 newtons on the ramp, determine the force that the motorcycle engine must apply to accelerate up the ramp at 1/3 g and assume that their mass is 250 kilograms. So there seems to be quite a bit going on here. It seems worded a little differently than normal, right? Would you agree? So let's draw a picture here and try to straighten this out. So here we have Evel Knievel on his motorbike, who weigh a combined 250 kilograms. There is an FD down the plane due to gravity, and there's also a FF, which we know to be a constant 1,000 newtons. And his bike is providing some sort of applied force due to the engine that's accelerating him up the ramp so that he can jump the fountains at Caesar's Palace. And what is that acceleration? 1/3 g. Now that's something that you probably haven't seen yet. What does that mean, 1/3 g? Well, regular g is 9.8, so 1/3 g is simply 9.8 divided by 3. That's all it is. It seems way more complicated than it needs to be. If it was 9.9, it'd be 3.3, right? But it's not, so it's a little less than that. So it's 3.27. So he needs 3.27 meters per second squared so that he's going fast enough so that he can clear the fountains at Caesar's Palace. Okay, and we are solving for what? Determine the force that the motorcycle engine must apply to accelerate up the ramp. We are solving for the FA. Do we know the F net? Not yet, but we can figure it out because we know the mass and we know the required acceleration, right? So our next step is to say F net is equal to MA, mass of 250 times the acceleration. You know what I'm going to do? I'm just going to put 9.8 divided by 3 in there too, so that I get a good value. I get 816.7. 816.7 newtons is the required net force. Is his engine going to require, is his engine going to have to produce more than that or less than that? More, because that's the net force when you account for subtracting FD and FF, right? Okay, FD is easy to find. FD is equal to mg sine theta, 250, 9.8 sine 30. I get 1225. Now, from a directional standpoint, that's down the plane, so what should I assign that sign? I should make it negative, right? Because it's down. Okay. Now, I already know that the question gives me that the friction force is 1,000 newtons, right? So minus 1,000. Oh, it's going to be long. Okay, so now let's go. F net is, we're going to add up all the forces that are acting. So that's going to be FA plus FD plus FF. And again, I encourage you when you do these kind of things to use positive signs here because you're really adding vectors. So my F net is 816.7. The applied force is what I'm solving for. FD is minus 1225 and FF is minus 1,000. And I really hope solving that is not a problem for you. Take everything to the other side, and you get 3,041.7 newtons of necessary force. Okay? Now, the textbook doesn't actually come out and do this, but I like to sort of add this little bit in here because I know that you're going to see it in the future. The question says that the friction force is a constant 1,000 newtons. Generally, that's not sort of how we do things. Usually, you're going to get the frictional coefficient, right? So what would happen if, I'm just waiting to see, is everyone done with this? What would happen if rather than 1,000 newtons force, the frictional coefficient is 0.15? All right, so how do I solve for, let's assume that the FD is still that same number, 12,225. Oops, where'd it go? And the F net was that 816 number, 816.7, right? But now let's try to come up with a friction force given the frictional coefficient. Mu equals FF over Fn. Do we have the Fn? We do not. Fn is going to be mg cos theta. So that would be your 250? 9.8 cosine, can't remember these numbers. 30. Okay, so if the frictional coefficient is 0.15, 250 21.8. Now you're going to go mu equals FF over Fn, 0.15, solve for friction force. In other words, you're just multiplying that number by 0.15, 318.3. Okay. And then you would just do what? The same thing, that last step, exactly, right? You would redo, whoops. You'd redo this part right here, right? The only difference being now, instead of your FF being minus 1,000, now it's going to be minus 318.3. So a little bit more sort of realistic type problem, I think. $23.60 newtons. Now, do you think a daredevil like Evel Knievel actually has a guy that figures this stuff out for him, figures out how fast he's got to go and all that? I'm thinking in this day and age they do. They didn't. I'm pretty confident when I say this. I think he just winged it. Kind of took a look at things, go about this fast. And this is the result of that thinking. So, I don't remember the year. Did I go too fast there, Mark? You good? You can Google it up if you want to read more about it. It's pretty funny. Page 196, 1 to 4. Page 224, 6 to 10. Those are in your textbook. Those are some extra practice questions. Tomorrow I need to start talking about statics, which is forces that keep things in place. I would really like to do that tomorrow for the last day of the week. I do have another pretest coming up. Let's do that first one. Get working on it. That's about it, really. Do I need to print some more, Mark?